So I'd like to announce that this course is extended for the next year. But since that's not practical, let me try to say several things quickly, and then of course we can have communication by email, etc. So let me start again with the map we looked at, which was the Bernoulli shift, for which we discovered the Lyapunov exponent. And I want to call attention to one particular feature of it, which is the following, and then take off from there. You see, this map, the Bernoulli shift, was not invertible. Because essentially what happened was that you drew this line, you cut it and put it back here, and that makes it a non-invertible function. This is a non-linear function. Although it's piecewise linear, it's a non-linear function. And this non-linearity, non-invertibility of the map is absolutely essential for you to be able to get all these properties such as chaos, etc. And it has a Lyapunov exponent. Log is log 2, losing one bit of information each time, etc. There are many other maps which also show similar behavior. And for example, here's one. If you drew this line 2x, but instead of cutting it and bringing it back here, you just folded it back. Just folded it back. Then the map you would get would be the so-called 10th map. This is Bernoulli. This would be the 10th map. And that would look like this. And basically the map would be f of x equal to 2x, or 0 less than equal to half, less than equal to x, less than equal to half. And 2 times 1 minus x for half less than equal to x, less than equal to 1. So it has a virtue that it's continuous. It doesn't have this nasty discontinuity. But it's also completely unstable in the sense that all fixed points are unstable. There's a fixed point at the point 2/3, but the slope is 2, so it's unstable. The first iterate of this map would spike with slope 4, 2 spikes, and so on. It too is completely chaotic, and it's not hard to show that the Lyapunov exponent in this case is also 2, log 2. That's because the slope always has magnitude log 2. If you like, the Lyapunov exponent in these one-dimensional maps is the average value of the stretch factor, and the stretch factor is the log of the derivative modulus of f prime of x. And if that's a constant, then it's a trivial statement that the Lyapunov exponent is just log 2.
What is meant by stretch factor?
The local stretch factor, if I change variables from x to f of x, then the Jacobian is f prime of x. And log of the modulus of that tells you how much it stretches or contracts, the exponent. Okay? We're trying to say that dx goes to df of x, and if df of x is e to the lambda times whatever it is, lambda t times this, you're trying to find what that lambda is. So the logistic map had fully developed chaos. This is the logistic at parameter value 4, was a curve like that, has the further virtue that not only is it continuous, but it also is got a derivative everywhere as opposed to this. So it's getting smoother and smoother on this side. And this one also is all the standard properties, and it was f of x is equal to 4 times x times 1 minus x. Now all these maps are not only chaotic, but they have the peculiar behavior that you can explicitly write down x sub n as a function of x naught. You can in that sense solve it. So you would say naively, it's integrable, I can write a formula down. But because it's discrete dynamics, the fact that the error amplifies by 1 bit at each iteration is explicit. So there's a 2 to the n epsilon, there's a log 2, and so on. So this is a misconception that people sometimes have, that you cannot, I kept saying that for differential equations, you can't write a closed form solution for the solution in T for the dynamical variable, and that means that the system, if it's chaotic, you certainly can't write down such a solution. But that's not true for discrete time dynamics. You may be able to write a closed form solution down, but it's got still chaotic behavior. And that's illustrated by these maps. You could ask, what about another class of maps which don't have a finite slope, but maybe an infinite slope, and so on. There is such a famous map. It looks like this. It's called the square root. It has very, very interesting properties of its own, which I'm not going to talk about here. And it looks like this. here's the unit, here's the bisector, and then it starts at slope 1 and goes to infinite slope there and comes back in this fashion. It's symmetric. Now, such a map displays another phenomenon called intermittency. It's intermittently chaotic. The physical reason is the following. Once your iterate gets stuck in this neighborhood, you got slope 1, but it's greater than 1 always, tending to 1 at this point. Therefore, it's a marginal fixed point, marginally unstable fixed point. But once the iterate gets stuck here, it kind of does this staircase behavior. So for long bursts of time, it looks like the motion is regular. And then, of course, it gets injected out of this region, back in here, etc. So in such a map, there will be long bursts of laminar behavior. And this is called type 1 intermittency. So the map is solved, everything is known about this map. A lot of things are known about it, but many things are still unknown about it, such as exact expressions for its correlations and so on. But physically, what happens is, you normally expect it to get stuck here and remain here. But it doesn't, because occasionally when it wanders out, it gets re-injected at rare intervals. But the collection region from which it should be collected to be re-injected should be appropriately small, otherwise the invariant density becomes a delta function here. And that's assured by having an infinite slope here. It becomes infinitely thin at that point. And now, in fact, if you give me any degree of tangency here, I can solve what's called the inverse Frobenius-Knorr equation and give you a map. So you give me a function which is invariant density, and I give you a map with all the desired properties. So a lot is known. This map, for example, is like 1 over, it goes like 1 minus 2 square root of mod x, or mod x minus half, or something like that. So these are analytic functions known for all these maps. They're all fully chaotic. Incidentally, I call attention to the fact that this map can be written down and connected to the Bernoulli shift very easily. Because if you have a thing like xn is 4xn times n minus 1, n minus 1 times 1 minus xn minus 1, this implies if you put, for instance, xn equal to sine squared theta n, if you did that, then it's trivial to see that the map reduces to theta n is twice theta n minus 1. Modulo 2 pi, of course. Modulo something like that, pi or 2 pi.
Sir,
Yeah.
sorry to say that I can't guess the idea of intermittency.
You can't get, yeah. So in an intermittent map, what happens, in an intermittent, very crudely, if you have a variable x of t that is undergoing intermittency, chaotic behavior is sort of completely, totally chaotic, irregular. But then, and then it will do this again. This looks almost like periodic behavior. So intermittency is chaos, but intermittent chaos is long bursts of regular or periodic-like behavior, but eventually it will become chaotic. There are several types of intermittency. The simplest type is this, it's called type 1 intermittency. It happens due to these little tunnel regions.
Only some part of the periodic motion it looks like a periodic.
Yeah, it will look like a periodic motion for long times. And then there will be long times without any periodicity. And the most famous example in practice of chaotic intermittent behavior is a leaky tap. The leaky faucet, if you control conditions carefully, there are hundreds of variables which control the rate at which drops fall out, the surface tension, the purity of the water, the nature of the boundary, etc., and the temperature. And then you can adjust things in such a way that long times you will look like, the drops are coming regularly, and then you discover suddenly they have disappeared, they become irregular. Then again it builds up, etc. So it's known to be modeled by an intermittent process. Yeah.
Can we say the same thing for our solar system? For our solar system?
Our solar system is almost certainly chaotic. Yeah.
Is this the periodic motion of planets?
Yeah, that it looks like, I won't say it's, I don't think it's intermittent. What I think is true is that it's got a Lyapunov time, which is very, very long, of the order of tens or hundreds of millions of years or more. So that's the reason why it looks very regular, but it's just too complex a system. In the old days, people used to worry about the stability of the solar system. And then there were lots of results, and finally the best result, I think, was that if you have a solar system with 7 equal mass planets, then it's stable or something like that. But we know that it's chaotic, almost certainly going to be chaotic. And we already know, there's a huge literature on this, we know several parts of the solar system that are completely chaotic, like Pluto's orbit is probably chaotic. hyperon's tumbling motion is chaotic, etc. So I think virtually it's certain that everything is chaotic. The question is how regular, how long is the Lyapunov? So let's now do the following, which is, we have all these maps, including things which sort of map into the Bernoulli shift or something like that. Let's see whether we can make some sense out of this by deriving an equation for the invariant probability density. I give you a map and I ask what's going to happen over long times. Okay. That derivation is not hard, but formally it involves a little bit of technical tools. So let me do it in the context of one-dimensional maps where it's very transparent. So I have a map, x goes to f of x, and x is in some interval I. And now I ask, okay, what happens as points start getting iterated? And we're going to ignore the sets of measure 0, namely periodic points. Most points, typical generic points, are all going to be on chaotic orbits. How densely or how non-uniformly do they fill whatever space you want to fill? Now, once you have a map like this, you can say, look, if x goes to f of x, or a point y goes to f of x, I could ask, what's the density, probability density of the iterated point? So I start with a point y, just to distinguish it, you can see. And this goes to f of y. It goes to x equal to f of y. Well, let's do it in the language which you're familiar with. So I start with an x naught, that goes to x1 equal to f of x. I ask, I want to do this in probability language. So I give you a definite x naught, and I ask you, what's the probability density of x1? What would you say? I give you a definite x naught. That's a delta function, right? So the probability density, rho 1 of the point x1, 1 because at time 1, I want to keep track of that, of this point x1, which is what I call the variable at time 1, this is equal to a delta function of x1 minus f of x1. Trivially, right? It's a delta function. We like, physicists don't mind delta functions. Mathematicians severely object to them. They talk in terms of measures, but we work in terms of delta functions. Now I say, no, I was wrong. I didn't give you a fixed x naught, I gave you a distribution in x naught. I already gave you a set of initial points. Then what's the density in x1? Suppose I give you given rho naught of x naught. Then what's the density in x1? Yeah, so you convolute this, you multiply this by rho naught of x naught, and you integrate over x naught. Over this interval. So each x naught goes to its f of x naught, a distribution in x naught goes to corresponding distribution in x1. This.
So it's a delta?
Delta.
Oh yeah, there's a delta, all important delta. Now what's rho 2 of x2? That of course would be exactly the same as this. It would be dx1 delta of x2 minus f of x1, rho 1 of x1. And I plug in for rho 1 of x1 what I already know, this formula here, and you get a product of two delta functions integrating this guy. Right? And I can do this for all time. I can keep doing this. So you give me any initial distribution, rho naught of x naught, and I'll tell you how it evolves at time n. And to cut a long story short, it's clear that rho n of xn equal to integral dxn minus 1 delta of x minus f of xn minus 1 rho n minus 1 of xn minus 1 over this interval. But you could also write it in terms of what the distribution, initial distribution was. You could also write it as dx naught delta of x minus f n of x naught after n iterations, rho naught. You could also write it like that, except that this delta function is very complicated. It's the nth iterate of this initial function. So you can write it in either way. So in principle, if you give me an initial distribution, I can find out what the distribution is at any instant of time, at any time step later on. Unlike the case of equilibrium statistical mechanics, where you need an input from outside, a postulate of some kind to tell you what the density is, the invariant density is, here you're given a dynamical system, a deterministic rule, there's no input from anywhere else. You've got to find everything you want about the system from this input. And indeed you can. Now let's take the limit n tends to infinity. And you have to now make sure the limits exist, etc. If the limits exist, that requires certain conditions on these delta functions, etc., etc. If the limit exists, then it's clear that the limiting density, let's call it just rho of x, this thing here, must be equal to an integral. Let's distinguish this by giving another name here, delta y. X minus f of y, rho of. And this thing here is the so-called invariant density, because now it doesn't change under time evolution. You agree? If I can show that this limit exists, then that invariant density must obey this equation. Because when n goes to infinity, whether it's n minus 1 or n doesn't matter, and it's just one density over this interval.
Corresponds to equilibrium state?
Pardon me?
Corresponds to equilibrium state?
It corresponds to the equilibrium state, equilibrium distribution. It's invariant in the sense that under time evolution it doesn't change. Further evolution doesn't change it at all. I just call this variable y, and this thing here is the same as that, because n minus 1 is the same, and then n goes to infinity. Right? So now what sort of equation is that? Is it linear? Well, the unknown is rho of x. So is it linear or not? Why is it non-linear? Why is it non-linear? It's an equation in rho. Right? It's linear. It's very much linear. It's a linear equation. Probability densities rarely obey non-linear equations. It's a linear equation. Rho. Is it a differential equation? No, it's an integral equation. Is it homogeneous or inhomogeneous? Homogeneous, yeah. You can multiply rho by a constant on both sides, it won't affect it. It's a homogeneous integral equation with the kernel. This kernel here, k of x comma y, is a delta function. It's a singular kernel. The kernel is not square integrable, because you can't define the square of a delta function. So you have a apparently simple problem, but it's a very nasty problem. You have a singular integral equation. Linear but singular integral equation. And this is some integral operator acting on this rho. So this stuff is equivalent to saying some, in function space, some ket vector rho is some operator on rho. That's really what it's saying. Right? But this curly k is an integral operator whose kernel is this singular delta function. Now what sort of equation is this? It's an eigenvalue equation. And you want the eigenvalue of this singular kernel, you want the eigenfunction corresponding to eigenvalue 1. Moreover, you have some other physical conditions on this rho. It must be normalizable, so certainly you want this. You want to impose the condition of normalizability, so that the overall constant in rho is fixed. What other condition do you have to put on rho? It's a probability density, so it's non-negative. So you also must have rho of x greater than or equal to 0 for all x in the interval. So now it's becoming a non-trivial problem. You not only want an eigenfunction of this integral operator corresponding to eigenvalue 1, but you want it to be a non-negative integrable solution. Should be integrable and normalizable to 1. No guarantee that this exists or anything like that, especially because this is a singular kernel. So even if f of y is a nice, harmless, nice nonlinear function, you still have this very nasty problem of finding the eigenvalues of and eigenvectors of this nasty operator, integral operator. Even in the simplest of cases, like the Bernoulli map and so on, this operator has an infinite spectrum. But there's a theorem, a very useful and deep theorem, which says that if a solution exists which satisfies these two conditions, then the solution is unique. And that's a hard thing to prove, but it's a proved statement. If a solution exists which is normalizable and which is non-negative, then it is a unique solution. So that, of course, immediately makes physicists happy, which means if you guess a solution and it fits the equation, then it's got to be unique. So let's see what we can do with that. Otherwise, the set of eigenfunctions of this operator are fractals. They're very complicated fractals, even for the Bernoulli map. And people have studied that in some great detail. But let's see what happens for the Bernoulli case, Bernoulli map. Now, we know what f of y is. F of y equal to 2y for 0 less than equal to y less than half, and 2y minus 1 for half less than y less than equal to 1. So what does the delta function thing do? It says rho of x equal to, and let's draw the picture, it's helpful. It's this map here. So it's clear that there are two different functions, one for x less than half, or y less than half, another for y greater than half. You're asking, here's x, which is f of y, and here's y. And you're asking, you must always be on this curve, or on this curve. And it's clear that as y runs from 0 to half, x extends over the whole interval, doesn't get cut off. So you can just close your eyes and do the delta function integral, except that you'll have a delta of x minus 2y, but you want a delta function in y, and therefore it becomes half delta function in y minus x over 2. So this becomes half rho of x over 2. And then in this range, you again have a delta function, but now it's a delta function of x minus 2y plus 1. So now you get a half rho of x plus 1 over 2. That's where y fires. So that's the Frobenius-Perron equation in this problem has been reduced to this functional equation. And unfortunately for us, there are no algorithms for solving functional equations. How did that? Pardon me?
Rho of x we will provide. We will take some.
No. The rho of x must satisfy this equation. What my input is this. For each map, I put this in. And then I find out what's the solution of this equation.
Suppose we ask this question. We have interval 0, 1.
Yeah.
We start from some interval on this, in this 0, 1.
Right.
And what will happen after infinite amount of time?
No, I don't start with that question. I start by saying, I'm going to take an arbitrary x, any arbitrary orbit, and let it run forever. Okay? And then ask, what's the histogram of this x? How frequently do different intervals get visited? And that's what this rho of x is. Provided the x I started with is a typical one. So I should really do it by taking some other x and doing it all over again, etc. So I should average over all possible initial conditions, generic initial conditions, and then if this attractor is not going to break up the interval into separate disjoint parts, but the system is ergodic on this attractor, on this interval, then you're guaranteed that this rho of x satisfies this. Now the map could be such that some portions get stuck somewhere, other portions get stuck somewhere else, or some portions escape, and so on. I'm assuming that that's not happening. You'll come across a case of escape, you'll see what happens. Now my task then is to find this function, but I'm saying, look, it's singular because of this delta function, but let me put this f in and ask what happens, and what happens in the Bernoulli shift is this. It's a functional equation. And I want the solution of this which is normalizable and which is non-negative. But I'm also guaranteed that if I can guess a solution, the answer is unique. It's clear that rho of x equal to 1 is a solution. So the answer is unique. I can't always do this, but this implies that rho of x equal to 1. What is that? Therefore, I have a uniform density. I'm assured that if I take a typical initial point, then as time goes along, the invariant probability distribution is a uniform distribution on this unit interval. The moment I have that, I can compute the Lyapunov exponent. Because the Lyapunov exponent, if you recall, was a long-time average. Lambda was equal to limit n tends to infinity, 1 over n summation I equal to 0 to n minus 1 log mod f prime of xi. This crazy thing for each iterative. This was the case. But this, because the system is ergodic, I can replace this by an ensemble average now. And this is equal to an integral over the interval I dx rho of x, the invariant measure, multiplied by log mod f prime of x. That's what ergodicity means. It means you can replace time averages, long time averages, by ensemble averages. But now I put this rho of x equal to 1. And the slope is always equal to 2 in this map. So it immediately says this is equal to log 2. Exactly as we got before. And once you have this probability density, then everything is fine. I can compute anything. I can compute any function of the dynamical variable x. And then the next step is to start calculating averages, calculating correlations and so on. In this Bernoulli map, strangely enough, the correlation is not a delta function. It's not, this is exponentially damped with log 2 as the characteristic time. It's not a delta function. You'd think that it's very random and so on, in a sense, which I will talk about in a few minutes, but it's still got an exponentially damped correlation. But you could ask, can I play this game for other maps? Can I do this for the logistic map? And so on. Then the matter becomes non-trivial. By the way, this 10th map, I leave this as an exercise to you to do. If you took this 10th map, this function is 2x here, or 2y if you like. But here it's twice 1 minus y. You'll get a slightly different functional equation. But again, the solution is 1. Once again, it's 1. Then we ask, okay, what about the logistic map? Which is, after all, topologically conjugate to this Bernoulli shift. What happens there? It turns out to be slightly non-trivial. Because now, look at what will happen. This is your map, this is y, this is x, f of y equal to x, and it's 4 times y times 1 minus y. Then your delta function constraint, you integrate from 0 to half, half to 1. When you do the delta function constraint here, not only is the slope not a constant in this map, but it's a Jacobian, because you will have a delta of x minus f of y, where f of y is a quadratic function. And of course, if you solve this, you're going to get delta of y minus y1 of x, which would correspond to this branch. For this x, this is y1 of x, divided by mod f prime of at the point y1 of x. To do the delta function, plus delta function of y minus y2 of x, which is the right branch, divided by mod f prime of y2 of x. So you find the slope and then you substitute this value here. And this is the point y2. X. And this is y1 of x. They'll involve square root of 1 minus x and other garbage. So if you do that, you have this term and this term. So your functional equation will become much more complicated. It will have functions of x sitting in there. No way to guess the solution. There's no simple way. In the Second World War, during the Manhattan Project, von Neumann and Ulam needed to have random numbers generated. And the popular method then was to take a 4-digit integer, square it and take the middle 4 digits, which for some weird reason they felt it was a good random number generator. So not good enough for their purposes. So they cooked up this map. This is also called the Ulam map. And not only did they cook it up, But of course, they connected it to the Bernoulli shift, and they found the invariant measure. They found the invariant density in this problem, not by solving the Frobenius-Perron equation, but by inverting from the Bernoulli shift. And the answer is the following. It turns out that in this map, rho of x is 1 over 5 times square root of x times 1 minus x. And this density is not uniform. You have 1. It's integrable because these are 1 over square root singularities, so it's integrable. It's non-negative. It becomes unbounded, but we don't care about that. The total area is 1.